in 1 plus 1d. I'll go into some more details in a moment. In 1 plus 1d Ising. Another kind of example is, say, Zn lattice gauge theory. In 3 plus 1d. All of these examples have a special feature that there's a critical coupling where they're invariant under a duality transformation. And this leads to a specific non-invertible symmetry structure, which I will describe in just a minute. And then that's the kind of key example whose anomalies we want to understand. There are other examples, but these will kind of guide our hand towards trying to figure out what anomalies actually are with these. So let me just unpack these examples and something a little more, give you some more details. So let's talk about duality defects. And so this will be sort of the general class of constructions of which this is the simplest example. So we'll have a 1 plus 1d QFT. And it has an abelian symmetry G. And associated lines L sub G. And we'll let's call this QFT T. We'll consider the kind of orbifold or gauge theory T modulo G. And importantly, this also has the symmetry. That's not completely obvious if you've never thought about it. Usually you think that if you gauge something, you might remove the symmetry. But here we get a new symmetry acting on the twisted sectors, which is also isomorphic to G. It's not Pontryagin dual. It's the Pontryagin dual, but for a those are isomorphic groups as groups. How? G is abelian. Yeah. You pick an isomorphism. Yes, there's a choice there, and that choice actually there is some physics in that choice. Yeah, there is some physics in that choice. Yes, that kind of choice will be related to some kind of details of the F symbols of this category that I won't really define. But yeah, there is some choice there. Yeah. Okay, so let's consider, we're keeping going here. I'm trying to give you an example. This example is by now kind of well studied, but we're going to go deeper into it, so we need to have our fingers on it. So we're going to consider the situation. Say T is self-dual under this gauge. So T is isomorphic. Okay, so then we can make an interesting general class of non-invertible symmetries. I'll do it here. I don't know if anybody's online anymore. So what's the picture? Here you put T. Here you put T mod G. I'm making here a defect D. We'll call it D for duality or Dirichlet. And so here we have this theory. Here we promoted these this G symmetry to be gauged. So here we have some dynamical D fields. And along this defect, we impose Dirichlet boundary conditions. And because of this assumption, this will be a topological interface between a theory and itself. So whenever you have a theory that satisfies this kind of isomorphism, you'll get a very specific kind of symmetry with known fusion rules. Let's say what those fusion rules are.
I will specify what kind of boundary. Okay. Is that precise?
What this is here?
Yeah.
So this is a Dirichlet boundary condition for these dynamical fields. And because I'm talking about a finite abelian symmetry, that makes this topological.
So that just means that the gauge field
Yeah, exactly. Just trivializes that.
gauge field parallel.
Okay. A restricts here to be 0.
There are other boundary conditions possibly, other than the restriction for the dynamic equation.
You can consider a variety of boundary conditions. I want to do this one because it's a particular kind of construction that I'm aiming for. But yes, I mean you could in general try to explore other boundary conditions, and we'll see a little bit of that later. Okay. Okay, so why am I bringing this up? Well, there's this very general fusion rule, which looks as follows. Oh, okay, we have this one. We have this interesting one. And then, of course, the L's obey their complete fusion. So these are the new fusion rules involving this duality defect D. So when these labels G are in the group Z2, then that symmetry is realized by the critical Ising model. When they're in Zn, you can get that for, say, parathermions, and more generally, there are other examples. So this is a kind of universal construction of certain non-invertible symmetries that exists whenever you have theories that obey this condition. Any questions? Very foreign, very familiar. Not sure where to aim.
I'm going to explain where the fusion comes from.
Where the fusion comes from. I wasn't planning to, but I can say it in words. This one is from the Dirichlet boundary condition, because the gauge field trivializes there, and these symmetry defects, say on this side, are just the Wilson lines of the dynamical gauge field. So that's why it has this absorptive property. This one is maybe the harder one. That one, at least in this construction, I believe was first worked out in a paper by myself, Shu Hang, and several other excellent authors. The idea here is that you have D times D. That's like you have gauge theory in a strip, where you have Dirichlet boundary conditions on either side of the strip. And this is saying that if you have this partition function of gauge theory in a strip with Dirichlet boundary conditions on either side, you can express the partition function as a sum over Wilson lines, because the Wilson lines generate this symmetry in that case. So that's how to get this one. You have to understand where the fact that there's a 1 comes from still, the fact that there's no coefficient. But that's how to see that D times D should be a sum of the elements.
the Wilson lines going perpendicular to the.
Parallel.
And move those.
Imagine for concreteness that the geometry is like. We're in 1+1, so imagine the space-time geometry is a cylinder.
Yeah.
And there's Dirichlet boundary conditions on either side.
Yeah.
And I'd like to compute for you the partition function.
Yeah.
Right, so it's just a sum over the possible Wilson lines that I could have going around this circle.
But if we move those Wilson lines to the boundary, doesn't just get one. It's not the Wilson lines of the gauge field that you're summing over.
I am summing over these Wilson lines. I'm not getting your question.
Then I go. If I move them, the gauge field is 0 on the boundary. If I move the
Yeah.
Wilson loop to the boundary, don't I get one?
Yeah. But why? Why do you think that means the partition function is 1? No, I'm not saying it's the order of the group. I'm saying it's a sum over insertions of Wilson lines around this circle.
Well, you're summing over G bundles that are trivialized on the end,
Yeah,
then you have a parallel transport across. That's really comparing the trivialization. Something different. I agree, because some over.
The picture is that, so there's that cylinder that has a very short width. I think your question is that if you have a Wilson line in the middle, you push it to the either boundary, it disappears because of the.
You get one.
But that's consistent, but the statement is that that very short cylinder is equivalent to a sum of LG. And that's consistent with the fact that if you insert an additional Wilson line, it will be absorbed by it, because you have already sum over all of them. The statement is not comparing that cylinder with that cylinder adding an additional line. The statement is that that cylinder equals the sum over LG. And that's compatible with the fact that if you insert an extra line, it does nothing. I think that was,
But the sum was over lines.
Hmm?
The sum,
yes.
if I just calculate the gauge theory on this thin cylinder, right, it's a sum over. Also,
Yes, it's a sum over connection that's short cylinder
That's right.
as they reach the boundary condition. And the statement is that that sum is equivalent to inserting that sum over GL.
okay,
okay, yeah, I guess I did explain.
So there's a one question from online audience. So,
Yeah, can you hear me?
wanna speak up your question or type it.
Yeah,
Hello.
so my question is, hi, are there examples of duality?
You can
defects
speak
you
yourself.
can-
Speak.
Oh, can you not hear me?
We hear you now, sorry.
Oh, okay. Yeah, my question is, are there examples of duality defects constructed by orbifolding with a choice of non-trivial discrete torsion?
Yes.
Can you, what's an example?
What's an example? Well, what's the easiest example is maybe the question.
Yes, please.
Well, you need you need G to be sufficiently rich such that there exists discrete torsion to begin with.
Mhm.
So, but I think we gave a variety of examples like that, especially in higher dimensions. We gave a lot of examples like that. I kind of want to get to the anomaly part, which there's a danger that if I spend too much time giving many examples, I won't. So maybe let's reserve this question for afterwards. But the answer is definitely yes.
So I think
Okay,
the easiest answer is might be 2DC equals to 1 at the KP.
I see. Is it like overfolding the diagonal ZN Or maybe Z2 times Z2 or something.
Equaling Z2 cross Z2 with some.
Yeah, I see.
Yeah, but the fusion rule will be different from what.
Yeah,
we wrote.
Yeah, they won't be exactly the same. Yeah.
It won't be Tambari Yamagami.
Some generalized.
Some generalized thing. Yeah.
I see.
don't have the name. Yeah.
Okay, okay, thank you.
Okay, yeah, of course, right, the fusion rules, I have to justify that. Maybe, since we're ultimately also going to be studying, the case of 3+1D, let me quickly give you a kind of fast parallel discussion there, it's very analogous. So in 3+1D, so again, we'll have T, this theory, but now it will have a Zn one form symmetry. So that means there are surface defects, Zn surface defects. And we're going to consider the gauge theory, T modulo Zn1. And we'll be specifically interested in the situation where these theories are isomorphic. The natural uplift of the situation we were considering here to 3+1 dimensions. Now it's possible, but because we choose a one form symmetry, it's possible for this statement to be true. If we had chosen an ordinary symmetry, then the kind of the symmetry would change after gauging. And so again, when you have this situation, you'll have a self-dual theory with a defect that has universal fusion. I'll call it D. Sigma now lives on a 3-man. Okay? And what does its fusion look like? Well, in this case, the kind of D times D dagger, here D was equal to D dagger, D times D bar, here was a sum over group elements. And here we'll have a similar thing, we're gonna have a sum over one form symmetries. But that sum is a little bit different because the dimensions are different. So I'll write it this way. So these one form symmetries have defect U. It's the surface operator. And so this whole composite altogether is something that you could call some condensation defect. So this is the generalization of this kind of main fusion rule to this case in 3+1 dimensions. D times D dagger is a sum over surfaces, and we can interpret this surface as a so-called condensation defect. So again, the derivation of this is parallel to what we had before, which is that to derive this, you want to consider the gauge theory on a strip. Now it's a 3+1D geometry on a strip with Dirichlet boundary conditions. And it's a gauge theory with a two-form gauge field because of this. And so the partition function of that gauge theory is a sum over Wilson surface operators. And that's what this equation represents.
What's the support of this condensation defect?
Sigma. This 3-manifold. Yeah. So this is there's a nice paper by Shao, Sept, Nashri, and Rupadakis, I believe, discussing the kind of general class of these such defects and how you can make these codimension 1 defects from codimension 2 defects by analogous formula. Well, so yeah, so interestingly, so this can act on local operators, it's codimension 1. These don't act on local operators. So as a result, this acts trivially on local operators, but it acts non-trivially on extended operators.
You're thinking about just Yeah, probably, yeah, it's better, right? So,
No, this could happen even in a gapless phase.
but not in place. I don't know.
Yeah, that's compatible with being in a gapless phase. This was also compatible with being in a gapless phase over here. For instance, the critical Ising model enjoys this. So for instance, an example with this feature is the free Maxwell theory at special couplings. It's a gapless phase that has this theory. There are also other kind of non-free examples, but yeah, so this can happen in that's kind of where I'm going, is that we have this kind of abstract algebraic symmetry that we derive based on self-duality, and then we'd like to know what phases of quantum field are actually compatible with this algebraic structure, and how would we go about investigating it. That's the problem of anomalies in a sense. Okay, so let's kind of get right to it. Well, okay, so I have an hour and a half, so I might as well just use it. Okay, before really getting our hands dirty, let's talk about sort of one kind of RG flow that has this symmetry. So you should think of these symmetries, they're topological operators, so that they're symmetries like any other. They could be used to constrain RG flows, as long as they're preserved along the flow. So let's give an example like that and see how we would phrase such a flow using the language of these kind of symmetries. So let's imagine we have, this will just be an example, 3 plus 1D Zn lattice gauge theory. So at a special coupling, it's self-dual. Under gauging so let's draw a phase diagram and see how we would think about it. This is an ancient phase diagram, so not adding much to this. So here will be here's n. Here will be e to the minus 2 times n, where e is this coupling. Here is, by conventions, 2 pi. This is the value where this coupling where the theory is self-dual. So we'll draw this special line where we have this symmetry coming down. And the phase diagram looks something like this. So what is the picture? So for small n, so this is like, maybe you want to know, this is like 5, this is like 4. So this special point is not an integral value of n. So on one side you have a Higgs phase. On the other side you have a confined phase. And then for n sufficiently large, you have a kind of gapless window where you have something deconfined. Okay, so for small n, we have this, let's try to say it using this symmetry.
Sorry, can I ask, what is this?
What is
Means Zn lattice gauge.
yeah, I don't mean the topological lattice gauge theory.
I didn't think so.
I mean a theory where I have link variables that are Zn valued, but the I don't sort of impose the flatness condition. I let there's a kind of energetic term and there's a coupling that sort of, if the coupling is big, it would impose that it's a flat connection. If the coupling is not big, it's not a flat connection. And so then as I dial the importance of this coupling, I can get a phase transition. That's kind of what's happening here.
But it's a theory on bifolds with lattice.
Yeah, it's a very specific lattice gauge theory. It's funny to call it it's not a ZN topological lattice gauge theory though. But it has for one value, one extreme value of its coupling, let's say over here, it's this long distance theory is ZN TQFT. A ZN topological lattice gauge theory. That's this side. And this side is just the trivial theory.
When you say it's Higgs, it's charge and Higgs.
Yeah,
right? Oh,
Yeah,
okay.
charge and Higgs, yeah. Yeah, that's why this thing has a ZN one form symmetry. It's because from that point of view, the minimal charge is N. And in here, so in this area here, here when I say it's gapless, it's a U1 gauge theory. Right, so the theory that you're most familiar with, Dan, is the one that's kind of extreme on this window. Yeah.
But anyway.
Yeah, no, exactly. Yeah, toric code is like the 2+1 D version of this. Good. So let's say this phase diagram from the viewpoint of this fancy symmetry that we introduced here, which exists along this line. Okay, so this first order transition at small n, that's governed by spontaneous symmetry breaking of T. So here you can think that going from this side to this side is spontaneous symmetry breaking of this duality defect D. How to think about that? Well, the two sides here, they differ exactly by gauging this ZN one form symmetry. And exactly when I get to this point, it's like I have two ground states, one of which supports this ZN TQFT and the other which is trivial. They become kind of equal energetically important. So those are the things that are being swapped by the action of D. So that's why this is a spontaneous symmetry breaking phase there for this non-invertible symmetry D. Up here it's different. This vacuum of the gapless phase, gapless self-dual Coulomb phase. This preserves D. So that's not spontaneous symmetry breaking. And instead, we'll have, if you look at like the massive excitations up near the lattice scale, you have massive monopoles and massive electric charges, minimally charged N of equal mass if you sat at this point. That's what the D invariance means. They're kind of a representation of D because the vacuum is preserved by D.
Does D become no, it doesn't become S. D is not same as dominant. In the U1 gauge.
D is S.
Oh,
D is S. D is S combined with. It's not quite exactly S. It has a piece involving S. Yeah. So the coupling here is this E is also the coupling. I set my convention, so it's also the coupling here. So this Coulomb phase has E squared over 2 pi equals 1 over N. N is this N. So N is 1. That's the S invariant point. If N is larger than 1, it's not exactly the S invariant point. It's a point that's invariant under the composite of S and this gauging. So it's a slight generalization of being at the self-dual point.
happens this track is not going.
Well, that's why it's not at an integer value of N. So who knows?
Is it
I mean, it's this model really only makes sense for integer n. This is between 4 and 5.
Subset method, we can probably formulate the subset method. From the leader table.
Yeah, that might be so. Then I don't know. You might guess that there are some guesses if you, but
So it's not known if it's first order there. Or second order.
it's not known. We can talk about it in more detail. There's a lot of interesting questions like that in this neighborhood about sort of trying to make sort of second order phases that have massless electric and magnetic charges simultaneously. There's a general argument that if you have that if you have massless electric and magnetic charges, it has to be an interacting CFT. Probably know that argument. But it's very difficult to avoid it being first order because the Cohen-Weinberg transition is first order. So I have to somehow involve keeping the magnetic charges and electric charges equally important in order to avoid the fact that the Cohen-Weinberg transition is first order. Yeah.
What's the effective field theory to govern maybe the larger portion of the full phase diagram? So you are thinking mostly from some latest model that allows other than low energy TQFT.
Here, their mass varies, their kind of potential of these particle C's varies. And when I get near to this point, the electric particles condense. And their minimum charge ends, so that makes it Z and TQFT. This is first order line. So this is a Coleman-Weinberg type transition in like scalar QED. And over here, the magnetic analog happens. So here, the magnetic monopoles start to come down, and then eventually it becomes favorable for them to condense, and then I get this confined grid.
Magnetic multiple condense, that one is charge 1 or
Charge 1.
Charge 1.
Yeah. That's why this becomes just trivial. So this is an example of how you might interpret an RG flow using these enhanced notions of symmetry.
And how about the tri-critical?
Well, that's kind of what Max was asking. Nobody really knows because at best it's some non-unitary thing. Because probably because it's at a non-integer value, but there are analogs where you could try to make this tri-critical point occur somewhere that looks even integral. That you can generalize this picture, but it's very hard to make concrete statements about that. People try. Could be an interesting CFT. That's something to think about.
But let's not even discuss the CFT. What's the parallel theory that should be the same theory you just described, but move downward line. To the critical points.
Well, that's like saying you want to bring the electron and monopole down in mass at the same time.
Yeah.
Right. But whether you can really sustain them all the way to gapless or not is not obvious from this kind of diagram. Right. These lines are first order, so maybe this all just maybe they just jump. It's not clear.
Can I ask a question?
Okay, so so this was an example of a phase diagram. So I'm still in sort of an extended motivation, and now I'm gonna let me say some results, and then we'll say sort of how we would compute these results.
Let me double check. Is there some question online?
Yeah. So can I ask? So the result between 4 and 5. Does that depend on some details of the model of assumption? Because usually, the position of the transition, it's not a universal thing, right?
It's a very good question. Yeah, you can move the position in other models. That's what I was alluding to. You can try to make this transition occur at an integer value of n, and then you'll really face the interesting question about what's going on there. Yeah. So yeah, it's definitely not a universal statement that it has to occur. There's just in like the simplest kind of old school ZN lattice gauge theory that it happens to occur at a non-integer value.
I see. Thanks.
Yeah. Okay, so more generally, what do we want to do? We have all these interesting new algebraic symmetry structures, and we want to constrain QFT phases with non-invertible symmetry. So, for example, what kind of constraints might we derive? I'll write some examples. So if we have this situation and self-duality. So it turns out that a trivially gapped phase is possible only if n is so-called Pythagorean. That means that n equals 2 to the a times b1 to the b1 bk to the bk, where a equals 0 or 1 and pi is 1 mod 4 prime. That's an example that looks like kind of an anomaly, but a level of sophistication above what you might find for standard anomalies. You might ask another kind of question. You might ask about symmetry preserving gap phases. Could there be symmetry enforced gaplessness in these kind of models? A symmetry preserving, by that I mean D preserving. So something that does not spontaneously break D. This is possible if n is k squared times Pythagorean. So this is of course one possibility, but more generally n could be a perfect square. So those are severe constraints, the severe algebraic constraints. And one thing I'd like to explain to you is kind of the method by which you might understand such constraints, how much you derive them. These are some kind of things that we might like to call anomalies of these symmetries. And what's the framework for thinking about them? So let me ask if there are more questions, and then I'll go into some examples of anomalies and how we think about them.
You'd like to explain why you use the word anomaly?
Well, it's an obstruction. Well, almost by definition, I'll say, in the sense that it is an obstruction to a trivially gapped phase, in the sense that if n does not satisfy this condition, then the theory, a theory with this kind of symmetry that I wrote down, cannot be in a trivially gapped phase. So in that sense, it's an anomaly.
Will they also be equivalent to, I mean, I'm not sure in this example, but will it equivalent to say you cannot gauge this?
Excellent question. In general, no.
Right.
In
Invertible symmetry, I think they are.
the invertible universe, they're the same. In the non-invertible universe, they seem to be different. Shuheng is the local expert, maybe the only person who knows about this subtlety. I learned about it from him. Yes, these are. So the question was a very interesting question. So usually we define an anomaly, kind of the old school definition of anomaly is that it's an obstruction to gauging a symmetry. At the level of defects, that might be sort of summing over all possible insertions of these defects, condensing them. And later we learned that an anomaly is also an obstruction to realizing a symmetry in an invertible or SPT-like way. Those two notions were equivalent, but in the non-invertible universe, they're distinct. So my motivation here, which is what I just erased, is sort of the kind of RG flow tracking, sort of what invariance do we have along RG flows, and when can we say that symmetry, that a theory is definitely non-trivial read. For that, I want this notion. I want the one that obstructs trivially gapped phases. But there are other questions where you might be interested in what about gauging the non-invertible symmetry? So those are kind of distinct things now.
Are these statements going to apply to lattice models, or they only apply to field theory models?
They will apply to lattice models.
Because it wasn't quite clear from your last gauge theory, but it wasn't quite clear, like to what extent, this duality defect is topological there and so forth.
Yeah, you have to investigate when it's topological on the lattice. It's a separate question. And you also have to investigate something important, which is whether the algebra that I wrote down is really correct, or perhaps it now involves also lattice translations, which get washed out when you go to the continuum. And in general, it does involve lattice translations, but there are still statements like this.
Okay, so there's another question online.
There's a question from
Hi.
iPhone.
Yeah, that's Sal.
Oh, okay.
Can you hear
now-
me?
Yeah, I hear you now. Yeah.
Okay, yeah, sorry, I'm on my phone. So this counterexample with the non-invertible symmetry, being able to gauge it but having obstruction to a gap phase, like what's the counterexample? Is it this Fibonacci category example?
This is really a question for Shuheng. Shuheng, what is it's the Fibonacci one? Yeah, it's the Fibonacci.
But there, I thought you're kind of summing over like L squared, like the L being the topological line defect. I thought you're summing over all insertions of L squared, not of L. Because you're summing over like 1 plus L, right? And that's what you're saying can gauge it. But it sounds like there's like a, I don't know, confused language, like a subgroup that you can gauge. Like with a mixed anomaly, I can like gauge the anomaly free subgroup. So I can like sum over some subset of topological defect lines, but I can't sum over all of them. So with this like, so is it true you can sum over all the topological defect lines of this Fibonacci example?
All right. In Fibonacci, there's 1 and L, and that's all.
Yeah.
But
Yeah, so
all of them, because you are only gauging 1 plus L rather than 1 plus the complement vector times L. In any case, I think the point is that when you define anomaly as an obstruction to gauging, it's subject to the ambiguity about what you mean by gauging a non-invertible symmetry. Whereas the other definition, namely the compatibility with the triviality gap phase, is much more.
okay. I mean, I'm not against this without consider a new definition, but okay. Okay, that was my question. Thanks.
Yeah, the point is that there's an ambiguity in the other definition.
By the
Okay.
way, so just 1 million. I should also advertise there could be a seminar dinner if you want to join. I think we will prioritize those audience ask good questions.
Must have one question to be fed.
Yeah. Because I think we can count on the people who can join this.
If you want dessert. What if you want to drink? Okay, all right. Good. So, okay, so now let's get into this question of anomalies. So to do that, well, we need the kind of upgrade of anomaly inflow to these cases, and that's this symmetry theory. Symmetry. So this is a way of decoupling symmetry and dynamics, geometrically decoupling them. So we have our theory T that we wish to study, and it's going to be the boundary of some TQFT here. And there's another boundary somewhere over here, X. And this is something canonical and topological. So we might take this boundary to be, say, if we were talking about TQFT being like a finite gauge theory, maybe this could be Dirichlet boundary conditions. I think that kind of example. So we have this TQFT on this little slab. Here's the theory that we're really interested in, this T. But since it's a TQFT, you could think that, well, the width of this slab doesn't matter. So if I squash this back together, I'm just back to the theory that I cared about. So charged operators, of course, will arise from bulk defects that can end here. And symmetries will arise from defects that can go parallel to becoming. So what's going to be an anomaly? Why do I like this? Well, an anomaly is, as I was saying, an obstruction to an SPT or invertible boundary of this symmetry TQFT.
Invertible boundary.
What is it?
Invertible invertible.
What is an invertible boundary? Well, I want to know when, if I squish this picture, when is the result SPT in this dimension?
So you want the,
I want this to become invertible as a QFT.
sorry, there are two different things. You're calling T the dimensional reduction along that interval, or you're calling T the boundary.
Maybe I'm sloppily not distinguishing them very much, but really it should be the dimensional reduction.
So you're asking when we can express an invertible theory, when can we present an invertible theory?
Yeah. Now, this is a topological quantum field theory here, this symmetry topological quantum field theory. So it doesn't undergo any RG flow. So if I use this definition, anomalies are automatically RG invariant, and also invariant under any continuous symmetry preserving definition, deformation. So it has kind of the standard, this kind of definition has the kind of standard matching properties that you might like for anomalies.
The definition is of a yes, no, is there an anomaly? It's not a definition of some structure called the anomaly.
That's correct. I guess I would say that any obstruction. I don't have some grand mathematical theory of what the list of all possible obstructions are. But yeah, so it's this thing that you want to call the anomaly. Yeah.
Is there some notion of invertible anomaly, like some structure are invertible? We got two of those stacked.
In general, no. In general, part of the issue here is that there's this really nice simple thing that happens for ordinary symmetries, which is that these obstructions that I'm talking about form a group, and they have some kind of simple additive property and stacking and so forth. And here we don't really have that. We don't. Yeah. So you can think about it very concretely in terms of like a fusion category. Imagine you have a fusion category with some F symbols. If the elements of this fusion category are all invertible, then it makes sense to talk about zero F symbol, trivial F symbol. Right, kind of what trivial is, and you can go from there. But if it's just a general fusion category, then there's not really any notion of like the trivial F symbol. The F symbols just are what they are. So it's hard to say when it has an anomaly and when it doesn't. There isn't a natural group structure. Sure.
Another way to say it is that for invertible symmetry, in stacked system, both each with symmetry, it makes sense to consider the diagonal subgroup of G plus. The diagonal G. So that's how it is. In this sense, it is the diagonal subgroup. That's not the self analysis. So therefore you cannot function.
Yeah, that's another nice way to say it.
So maybe it must, if we have just ordinary symmetry, this kind of definition of anomaly works.
Yes, so here so how do I get back to the picture where you would think that you're talking about, you usually want to talk about inflow where the bulk is invertible, not a dynamical TQFT. Think of this as the Digraph-Witten theory, with the action term being what you would usually call the anomaly, and think of this being the Dirichlet boundary condition for that Digraph-Witten theory. Then the presence of this Dirichlet boundary condition just freezes these dynamical fields again. And so you get back to the standard picture that you were at.
I see. So something like say spontaneous symmetry breaking on the left boundary, that would still give you a theory which is has a degenerate balance theory.
Yeah, so this is really just, it's really just like the, for the case where we're talking about a standard invertible symmetry and anomaly, we didn't do much as long as I take this to be the Dirichlet boundary condition. But it's really this picture which generalizes out of that situation. Okay,
Sorry, which boundary is put in the anomalous theory?
this is sort of the theory, well, I'm being sloppy when I say sort of this is the theory we want to study. Really, it's like the whole squash, but this is like the canonical topological boundary, say Dirichlet in the case of finite gauge theory, and this is the other boundary that we're going to investigate.
Sometimes that right boundary is the maximum symmetry broken boundary.
Yeah, exactly. Yeah. In fact, that anticipates exactly what I was going to say next. Okay, so so I want to use this picture to do some concrete calculations in 1+1D, sort of tell you where some things come from. I probably won't have time to do any concrete calculations in 3+1, but I think when you see how it works in 1+1, you'll sort of get the idea. Okay,
Maybe
so
I missed at some point, but anomalies obstruction to have this symmetry TFT work or what? You put the obstruction.
no, the symmetry TFT works the whole time.
Right.
It's a question about what kind of boundaries of the symmetry TFT exist.
So obstruction to just maybe someone else, but
I think Dan asked me for
Yeah,
a
that's right.
clarification. Really the correct statement is that it's an obstruction to having an invertible theory that can be presented this way.
invertible in the bulk. Or
No, the bulk is this TQFT.
if it's not invertible,
Take this interval to be very tiny. It becomes a theory in one lower dimension. We wish to know whether that theory is invertible. Okay, so let's get serious in 1+1. I'd like to actually use some tell you about anomalies of those Tambara-Yamagami fusion categories that I wrote down. Okay, so here the symmetry is a fusion category. Okay. So we have fusion rules and some F symbols. What's the symmetry TQFT? This will be the so-called Drinfeld center. Okay, it will become clear why that's the case presently.
Symmetry TQFT is three-dimensional theory.
Yes, this is a 2+1D.
You say the theory is Drinfeld symmetry. So,
Yeah,
okay.
what does that mean?
Is that what's attached to the circle? Think of a Reshtikin drive. theory
Yes,
based on
yeah.
that modular. But it is the theory of fusion.
Yeah, if the fusion
Drive arrow theory.
If the fusion category was graded, it would just be like the double. Yeah. Okay, so so we want to study boundaries of this this theory. So first of all, when I present a theory this way, this A defines sort of the right boundary. It's the analog of the Dirichlet. That's where everything in A can end.
Like, that's not precise, right? Because A is not a.
It's not really a, no, okay, it's okay, if it's the double, then it's the things of the form, I don't even know, I don't even want to introduce labels for them, but it's the things of the form x bar that can end.
Yeah. There's a forgetful map from the other.
Yeah.
The image.
Where pre-image. Have to write pre-image on the board.
Isn't it relevant to say reducing A as a module category for some? Finds and boundary.
Yes, I think so, but I need to do some translation to.
If the bulk were 1 + 1 dimensional, they wanted a 1-dimensional boundary.
Yeah.
The bulk were given by an ordinary algebra matrix. Finite.
Yeah.
What would you say defines boundary? You say it was an algebra. Algebra, for example, a representation. So this is the same thing. Category.
Should be one. But I think we're probably right, but. Many people will say so.
Yeah, I'm about to say this, yeah.
I could relate. I mean, you clearly know this better than.
Oh, there's a theory about modular categories that relates to algebras within the category.
Importantly, here the boundary is not related to the module category.
Okay, so we want to study boundaries of this fellow here. So boundaries are in one-to-one correspondence with Lagrangian anyons. What's a Lagrangian? Well, it's a formal sum like this, with some coefficients, satisfying some properties. So these NAs are integers.
Although I should say earlier, but actually, so you can write a bit larger for those alphabets. I think the mathematical formula is all fine, but anyway.
Okay.
Not too late, guys.
Oh, okay.
The words.
This Lagrangian tells us in making the boundary who is going to condense, what kinds of particles are going to condense on the boundary. So these are the, if A appears non-trivially in this sum, that is, if little n A is not 0, then this condenses.
Random element of zero.
Yes, these are labels for A are the anyons in Z of A.
That means these are line defects. That can end on that.
Yes, and this little NA tells us the number of ways that they can. So this is like a boundary bulk fusion coefficient. So what to say? So there are some variety of properties of these things that are useful. So first of all the anyons in L need to have trivial mutual statistics. They can simultaneously condense.
In all channels, in all fusion channels.
I mean, they're braiding around each other is trivial.
Yes.
Yeah. Yeah. I was just thinking about a picture where you have the boundary here and you have two things that can end, and now you loop this one around the other one.
But they can fuse in several channels, right?
I'm
So-
braiding it around.
So R, A, B, C, right, depends on C.
It has to be trivial for everyone in here. When you restrict it to this
Let's
Lagrangian.
say that A and B part of that Lagrangian.
Yeah, and then restrict it, only look at the C's, which are also part of the Lagrangian. And then it has to be trivial. It also has to be maximal. So that means that the sum over, that gives you a sum condition on these coefficients. Has to be the square root of the total quantum dimension. So this is these are the quantum dimensions of these anyons. Good. So we want so that means in particular that if there's some anion that's not in L, then it will braid not trivially with something that's in L. So physically you think that these are going to condense, and then because of that property that I just mentioned, everything else will confine. So that's why a boundary is a topological boundary is labeled by a Lagrangian. That's the physical picture for that. There's some continuous data that I'm not writing here. That's also part of this kind of bulk boundary fusion that has some compatibility with the F symbols, but I won't need it for this discussion. Okay. Get it faster. Okay, so well, I kind of erased something that I wanted to say. So this C of A always has some Lagrangian, which I might call the electric Lagrangian. LE means electric. It's the one that we just talked about down here that we erased, which you could think of as a boundary which fully spontaneously breaks A. So for instance, if this was braided, then you could think that this was a sum of A now in A of A bar. In that case. So for instance, example. So E here is meaning electric. Since if it were a finite gauge theory, that would have been sum over the electrically charged particles.
In the parentheses, you assume A is a modular of its compatibility.
Braided, yeah. Okay, so we want this to find when we can make this slab a trivial picture with this thing on one side. This is our canonical boundary. So what do we need? So we're going to put some Lm here. Here's the TQ of T that we're setting. Theta of A. And here's LE, the other side. So to make this whole picture invertible, what we need is another Lagrangian, L sub m, m is for magnetic, which has the property that its intersection with LE is only the trivial anion, the minimal possible intersection. So this is a magnetic Lagrangian.
That's the only condition.
Yes. Yes, this is the general condition, that there exists a Lagrangian of this type. Then, for instance, there's nothing that can stretch across. That nobody can, except for the trivial line. Nobody who can mutually end here. So this is the condition. So when such an LM exists, then by the definition I gave of an anomaly, there will not be one. So this is the, if such an LM exists, that's the anomaly vanishing condition. So in this context, what we might say is that, well, what's an anomaly?
There's an online question.
Yeah.
Let's see.
Hi. Hi, hi, good. So can I make sure that the existence of the magnetic Lagrangian algebra implies the TQFT can be an invertible TQFT also applies to higher dimensional case? Or this is a special, or in high dimensional case, you have to impose more conditions?
I'm most confident. I think it is correct in higher dimensions, but part of the reason it's correct is because the higher dimensional TQFTs that you study are much simpler. Because
I think there is a counterexample, but maybe we can discuss it later.
Okay, that sounds interesting. Yeah, let's talk about it. Okay, yeah.
Okay.
Go for it.
A related question, which is a follow-up of Vinicius' question.
Okay.
Hierarchy, the cap boundary condition is probably not just specified.
That's correct, but that's kind of what I was meaning by sort of what kinds of TQFTs are you actually studying in higher dimensions. If we consider the
D2 gauge theory.
yeah. But imagine you first do, so let's reason a la Jauquet. So let's, instead of doing that example, I insist that we first condense all the particles. So now I've arrived at an abelian two-form gauge theory. In that theory, I can specify its boundaries by Lagrangians.
Is that the feedback or color feedback?
That you can
every two-form gauge theory, every gap boundary of a two-form gauge theory is uniquely specified.
Uniquely specified? No, there are probably additional choices. But if I find that there is no such Lagrangian, then I have an obstruction. That's the way I want to use that. Yeah. Okay, thank you for that point. That's kind of more relevant to the 3+1D example. But let's keep going with this. So anomalies here. In this case, it's something you could like find, which is an obstruction to LM. Now, why do I keep saying obstruction? Why don't we just make a list of all the LMs? It's because, in order for this to be a useful definition, it has to be kind of computable, right? It's not just anomalies of invertible symmetries are great because we can get our hands on them. And we'd like this to be sort of similar. So I don't want to make a list of LM. Constructing the LM explicitly, that's like explicitly constructing the invertible phase, realizing the symmetry. I don't want to do that. That's too much. Right? I want to constructing that phase. That's much less information. Okay, so in the last 15 minutes, I'm going to say sort of sketch how you would do this for Tambari Yamagami. Okay, so we'll do an explicit example and then we'll come. So Tambari Yamagami, that's the fusion rule for this 1+1D self-dual theory. That's the fusion category for that. These fusion rules I wrote down. And G here is the abelian group. How do we construct this? You can construct this in 3 steps. So first you begin with untwisted, say, 2 plus 1D G gauge theory. That would be the right fusion category if the right symmetry theory if we didn't have the duality symmetry. Next, you pick a Z2 symmetry. This will be the duality that permutes the anyons. So once I have this, I will have a symmetry, a Z2 symmetry enriched G gauge theory. And then finally, I'm going to gauge this Z2. Each of these two steps involves some choices. Here I got to choose which Z2 I was calling the duality symmetry. So that choice will be some label of this result. Here I also have a choice. This choice here, what choice do you have? You can stack with a Z2 SPT before you gauge. So that would be labeled by, in the bosonic universe, H3 Z2 U1, which is C2. And this is sometimes called the Frobenius-Schur indicator. It's what shows up in the file, it's the F symbol that shows up in the following crossing. So we have D, 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 D. This is epsilon, which is a sign, plus or minus 1, over the quantum dimension of D times the reconnected version.
We assume that G is
abelian.
not non-anomalous by itself.
Yeah, untwisted. Yeah.
Sum over the channel right inside of the.
This is just the 1-1 channel.
So you didn't write every term.
I didn't write every term. Yeah,
That's
sorry.
the first time.
Yeah, sorry. Yeah. It's this particular term in this sum. Yeah, thank you. Yeah. Okay, so good. So now we want to find in this scenario when are there or not obstructions to LM, the existence of an LM. So there will be kind of two steps of the obstructions. We can think of, because we have this presentation, this nice sort of 3-step procedure, we can look at first sort of an obstruction that talks to these two steps, and then next an obstruction that knows about this step. Okay, so kind of obstruction 1. So in this G gauge theory, there must exist a Z2 invariant LM, just within the gauge theory on its own. Otherwise, the gauge theory itself can't have the duality symmetry. The kind of the theory of the theory of just the G symmetry can't have the duality symmetry. So for instance, if G is Zn, G is Zn is always anomalous because of this set for any n. Okay, maybe I 5 minutes, so I leave this as an exercise. more. So there's not even sort of magnetic Lagrangian at the level that's Z2 invariant for this G gauge theory. And what that means is that when you have Tambari-Yamagami symmetry where G is Zn, you always have symmetry enforced gaplessness, meaning that either the duality symmetry is spontaneously broken or the theory is gapless. There's no other possibility. So for instance, in the critical Ising model, you can have the duality symmetry if the theory is gapless, but you cannot have it otherwise. Otherwise, you spontaneously break it. And that's true in the Zn analog as well.
Choose by the homework. So when n is greater than 2, can I take the Z2 charge computation?
The Z2 charge computation.
When you say Z2 invariant, you mean the Z2 0.
Sorry, the Z2, sorry, I should say which Z2 I'm talking about. Sorry. Here, this is the, so I should, yeah, so here for G is Zn. I mean that there's anyons of the form e to the a, e to the p, m to the b, m to the q, where p and q equals 0 or n minus 1. And I'm considering the particular duality symmetry, which exchanges e and m.
So in the second bullet point, there is not any that we're using.
Well, you could try to make Tambari-Yamagami for any Z2, I think, using this procedure.
Right.
But I'm particularly looking at this duality one, so we would naturally call electromagnetic duality, and then this.
Then
Yeah.
And the chart conjugation that wouldn't be non-invertible at that thing.
Charge conjugation. Not be none.
It depends on.
It might depend on n. It might also, I mean. Let's talk about it afterwards, but yeah, it's a good question. Yeah.
You start with Z2, then that's.
Yeah, so I think it kind of makes it into just into the fusion algebra of a non-abelian group is the answer, and which is a non-invertible fusion algebra, right? That's like the representation ring of the right. So yes, it does make it non-invertible. It just doesn't get exactly this kind of same kind of constraints that we're talking about here. So it's a fine example.
It might end up being no.
It might end up being non-anomalous, yeah. Okay.
Sorry, just make sure. I think
Yeah.
you say that I didn't really get it. Z2 invariant means invariant under EM relabel.
Invariant under switching E and M. Yeah, so I have a list of anyons that's going to be in my magnetic Lagrangian, and it has to satisfy all the properties of Lagrangians that I wrote down. But then it also has to be invariant under swapping E and M. And you can just check that there's no such magnetic Lagrangian. Right. The only, more concretely, the only magnetic Lagrangian, something that intersects trivially with the electric one, is just the sum of the magnetic particles. That's not duality invariant.
But let's just make sure. So like Z2 torical will not satisfy this. Z2 double semion. Just a simple example.
That's G equals Z2, yeah.
Right. So that I think these are the simplest example. The 1 plus 1 the example.
Plus 1 being example.
What the Z2. Let's say you have I think in your first paper on this non-invertible symmetry anomaly 1 plus 1 you have the example that you enumerate the Z2 torical and Z double semion. So in terms of that, what's that condition being satisfied or failed for them? So for torical we have Z2 torical we have LE and LM, right?
Yeah, E and M here is what I call them.
And do they satisfy Z2 invariant?
No, the Lagrangians there are very simple. There's no the only one that has the property that it intersects trivially with all the electric particles is the one that's composed of only magnetic particles.
Yeah, there the LE and LM both LE consists only electric particle, LM consists only magnetic particle. So
Yeah.
that's satisfied. So
Those are both Lagrangians,
right.
and that LM intersects trivially with LE,
Yes,
but it is not Z2 invariant because it is not invariant under switching the labels E and N.
that's right.
And I'm saying that that feature is a general feature for any Zn. If you want to sort of get past step one, you have to get you have to be in a richer group for this. Okay. Yeah. I'm practicing giving a 90-minute talk, so I don't know how many pages in my notes is 90 minutes. So I guess I'll sort of maybe just say the rest of the results. And not compute anything. Okay, so for Zn's times Zn, we'll not say it. Here, it depends on. So I highlighted this choice that about the which Z2 symmetry you might be talking about. So here we have particles E1, E2, M1. M2 as the generators. And we can talk about a diagonal one. And we can talk about a which switches diagonals E2, E1 with M1, and E2 with M2. Another interesting choice is something off diagonal, which is E1, M2, and E2 with M1. It's another Z2. And now the answer to this kind of first obstruction depends on which you pick. So here you have no LM unless N is Pythagorean. And here LM exists for all N. Once you talk about the first obstruction, then there's a second obstruction to discuss. That's the epsilon that I told you about. That comes from the epsilon. And it comes from the fact that in the Lagrangian that we want to make a Lagrangian for Tombari-Yamagami again, not just for G-gauge theory. In that Lagrangian, we're going to need all the particles to be bosons. And we can therefore get obstructions by inspecting the spins of various anyons and demanding that there are enough bosons. So in obstruction 2, which is the last thing I said. Epsilon, this FS indicator. So here, so this controls the spins of the duality matrix. So make the table for you and see, you can kind of see how it works. N equals 2, epsilon equals +1, N equals 2, epsilon equals -1, and odd. And even. And odd. I'm not doing all Pythagorean, just some smattering of examples. So this is the table. We'll have the number of bosonic kind of duality anyons in C of Ty Cn times Cn. Okay, what you get 2, 3, there's some calculation you have to do. 0, 2n minus 1, 2n minus 1, 0, 0. some calculation of the spins that you could do in this theory. And this leads to further obstructions, in that it's not difficult to show that the Lagrangian has to include a duality anion. It's not very hard to show. On the other hand, if there aren't any bosonic duality anions, they definitely can't be in the Lagrangian. So, for instance, this case has an anomaly here because of that, because there are no bosonic. So this is anomalous. Because there are no bosonic duality anion. This case is also anomalous. And in this way, we can actually reproduce Tambara's results about when fiber functors exist for this fusion category. So he did more. He actually constructed fiber functors, but I'm giving a kind of simpler argument for when they don't exist. Okay, so we have these two levels of obstruction. The first level is finding the Z2 invariant, the duality invariant magnetic Lagrangian. That gives you a chance. That's kind of an easier thing to compute. Yeah.
So the first step, you're trying to find such an LN G gauge.
Yes, exactly.
But eventually you gauge get to a different. But now, are you assuming that all the gap boundaries of the string field center where Córdova and Anomalies come from the gap boundaries of the like, is it possible that when I
Is it possible
these like again
I think not that are relevant to this discussion. I don't want to make a general statement. The reason I think not relevant to this discussion is that here, if I put this, if suppose this doesn't exist, what does that mean? It means that the G gauge theory, it means there's no invertible G phase that's duality invariant. That's what it means. Right? That's the condition that you and I talked about in our paper, right? So I'm first checking that by doing this. So I think for this analysis, it's a correct first step.
But let me just make one quick comment. That
Yeah.
Let's say we're in 2D theory, there's the feature levels.
Yeah.
Then before gauging, we can have a pair of boundary condition exchanged by the and after gauging, it becomes two. But I see your first argument because now that you said it, it's the same condition we checked.
Yeah, it's the same condition we checked. Yeah,
But
exactly.
it's not entirely clear why we are not listing any other candidate boundary conditions.
Well, it's like because well, we might be missing some boundary conditions, but I don't think they can be relevant to this question. It's sort of what I would say. I don't want to make a general statement that all boundaries are captured by this, but definitely the ones that are relevant to finding anomalies, I think are captured by this. Okay, so anyway, we have these two. Just to sum up, I'm over time. We have these two levels of obstruction. Finding first step is finding magnetic Lagrangians in the G gauge theory, and that's sort of where you get these funny number theoretic conditions from. So that these constraints on N pop out of this step. And then the second constraint is if you satisfy that, there's so maybe I should pause to say that step does not exist for invertible symmetry. That's kind of interesting. So this is like a step that sort of only involves the fusion rules. And that step for invertible symmetry, fusion rules are never anomalous. It's always about the F symbols. So this step kind of has no analog for invertible symmetry. But this step is like inspecting the F symbols. This is much closer to what we would normally do to find anomalies of invertible symmetry. We would look for the F symbols. When do they form some non-trivial group cohomology class? Here I'm doing something very similar. I'm asking about when do the F symbols satisfy some very certain properties. Okay, so that's how you apply this machinery in practice. And if you're interested in the 3+1D version, well, there's a paper about it. It's kind of simple. Okay, I'll stop here. Yeah, go.
The 3+1 in our paper, we essentially did the first step.
Yeah, we did the first step. Yeah.
So logically, it would be that in the second step, there are more.
And there are.
Anomalous.
There are. Yeah.
But so when you look on that conditions on n, so that condition is more stringent than the one we have. Is
No, I wrote two things. So that I wrote that n has to be Pythagorean. That's what we had.
that's what we have.
You're right. And then, but then I wrote that if you want symmetry, symmetry enforced gaplessness, sorry, if you want a symmetry preserving TQFT, then you get a weaker condition. That can also be seen from this Lagrangian
So
analysis.
if I only care about the anomaly, then
Yeah, the invertible case, then it's the same.
then it's the same.
Yeah.
I see.
Then that gives the list of n's that we found.
Right.
And you can do it for ST invariance or S to the n, whatever you want. But it's the next step that we didn't do. And there's a next step. So the next step, so in that step, you'll need to take care of stacking in this language, stacking with a Z4 SPT before gauging. Z4 because duality is order 4 in this dimension.
But sorry, the second step is still about the anomaly, but not the symmetry.
Sorry, do you want to know what the second step is in 3+1D, or you want to know about the symmetry enforced gaplessness?
If I only care about anomaly.
Yeah, then forget symmetry enforced gaplessness.
Right, forget about symmetry.
Uh-huh.
3+1.
Yeah.
Then there are still two steps.
There are still two steps.
Right.
The first step is something that we already did. We phrase it in a different language, but we did it.
But then, just for the purpose of anomaly.
There's a second
new
step.
Information.
Yes, there's new information.
Straight from the second.
Yes.
But why is the end result the same?
Oh, sorry, I was neglecting that information in that statement. I was just saying, I was just saying that as an.
Saying that they are anomalous.
Yeah, they are
There
anomalous.
things that are
Yes,
anomalous.
yes.
Oh, I see.
Yes,
I see.
yeah,
Okay.
yeah.
Okay,
yeah. There's a non-trivial second step.
okay. So there are more values of n that are anomalous than the one we found.
Well, no, it depends on the FS indicator. So it's not only a function of n anymore,
It's not a- okay.
right? Just like here, where I can get different answers for the same n.
Oh,
Yeah.
I see.
Yeah.
So questions here, response was something about S2 level 1. With S2 goes into.
I think that was Shu Hang said something about that.
What was
Somehow is there some interesting like CFT is into for C2?
yeah, the these people one that taking one.
Yeah.
Applies the self.
That's the one that's invariant under gauging with SPT. Yeah,
That's the one that's invariant under gauging D2 cross D2 with potential. At that point, it's a trial. Future is different.
The usual case is that.
If I remember, somewhere on the sequence of the I think it's
so that part for sure, but which point I don't. Yeah.
I think if I find.
Yeah. So it's kind of like a general. So the kind of interesting non-invertible symmetry here was order 2, and that one would be order 3. Order 2 meaning like D times D was the sum of the invertibles. There'll be some kind of analog of that for something like D cubed in the triality case.
There's an analog of that for the 3+1 D maximum.
Yeah.
Where you don't go to the multiple of the self-fuel point, you go to the triality. It's an integer constant biology.
Any other questions?
Any more questions? Comments?
Everybody's exhausted.
Well, I think we should thank her again. Thank you.
Shuheng even answered some, so he gets to drink if he wants.
I'm not there.
But fortunately,
You're going.
I'm not a fan.
Yeah, I'll see you. Yeah, I'll see you.
I think you can bring your wife.
Thanks.